So in this video, what I'm going to do is I'm going to go over how to draw the molecular orbital diagram for a heteronuclear diatomic. So in this case, it's going to be NF, right? So nitrogen fluoride. So if we were to just draw out the Lewis structure in this case, right, what we have is nitrogen right here, we have fluorine right here, and so what we would end up with is a double bond, and then two lone pairs on each one, and then the nitrogen should have a negative formal charge, and the fluorine would have a positive formal charge, right? So both of them now meet the octet rule, right? There's 8 electron pairs around the nitrogen. There's 8 electron pairs, not 8, sorry, 4 electron pairs around the nitrogen, 4 around the fluorine. So both of them meet the octet rule in this case, right? And then we have our formal charges drawn out. So the way to approach these types of problems is first off to, essentially put the nitrogen on one side and then the fluorine on the other side of your piece of paper, right? And then at the end, right, what we're going to draw is then the MO diagram in the middle between the two of them. So the first thing to do is you're going to draw out the atomic orbital diagrams for each one of those individual atoms, right, for the nitrogen and the fluorine. Now, one thing to point out is that they're not going to have, right, so both of them, for their valence orbitals, right, they're going to have the 2s and the 2p. However, those 2s and 2p orbitals aren't going to be at the same energy for both of them, right? The nitrogen is actually going to have higher energy 2s and 2p orbitals compared to the fluorine, right? And that has to do with the fact that the fluorine is more electronegative, and so more electronegative atoms have their atomic orbital energies lower in comparison to ones, right, that are less in electronegative. So the way that kind of plays itself out in the MO diagram is that, if I were to start off, I would just start off with the fluorine first to kind of give myself an idea of where the spacing of everything is going to be. So I'm going to have the fluorine right here, so I have my 2s here at the bottom, and then right here I'm going to have my 2p's, right? So 1, 2, 3 in this case. And so then now here for the nitrogen, right, I would expect that to be below the 2p for the fluorine, but above the 2s, so kind of somewhere around here. And then I would expect my 2p for the nitrogen to be above the 2p of the fluorine. So somewhere around right here, so. Right? So those are going to be, those are the two atomic orbital energy diagrams for each one of the individual atoms. Next thing we want to do, right, is we want to put in the number of electrons that we have for everything, right? So in the case of the nitrogen, right, nitrogen has 5 electrons. So if we use the Aufbau principle and Hund's rule, the Pauli exclusion principle, sorry, right, what we get is an atomic orbital energy diagram for the nitrogen that looks like that. In the case of fluorine, right, we have 7 electrons. And so what we're going to be doing is putting those in. So, right, so what we end up with is something that looks like this right here, right? So those are the atomic orbital energy diagrams for both the nitrogen and the fluorine. Now the thing that we have to think about is where do the molecular orbitals end up, right? So in the case of these right here, right, we would expect the 2s's to interact with each other. So we're going to have the sigma bonding orbital for these combinations be below the lowest energy atomic orbital that's contributing, right? So we would expect the sigma bonding orbital to be below the 2s of the fluorine. So we would expect that down here, right? I'm just going to draw lines to kind of signify where everything is. And then next, right, we would also expect, right, if we're going to be making a sigma bonding combination, we also have to have the sigma anti-bonding combination. And so that's then going to be higher in energy than the highest energy atomic orbital that's contributing, right? So in this case right here, that would be the nitrogen 2s. So we would expect that sigma anti-bonding orbital to be above that. So we would expect that to be about right here or so. I didn't really give myself a lot of great room, so that's definitely slightly higher in energy. It's not the best drawing, but it's just how it goes. And so this contributes right here, right? So this is going to be the sigma anti-bonding orbital between those two. Next, the thing to think about is that we're going to now have the interactions between the two 2p's, right? The 2p on the nitrogen and the 2p on the fluorine. Now, if you've looked at the homonuclear diatomic molecular orbital diagrams for dinitrogen and difluorine, one thing that you should see is that in the case of dinitrogen, right, we have that weird trend where it kind of goes sigma, sigma star, pi, sigma, pi star, sigma star, whereas in the case of the fluorine, right, it goes sigma, sigma star, sigma, pi's, pi stars, and then sigma star in that case, right? So on the homonuclear end, right, they look different in terms of what the ordering is. Now, the easiest way to approach and think about this then is that we would expect the orbitals to actually then follow the nitrogen pattern in this case, right? So the next orbital after that sigma star we would expect to be is going to be the pi stars. Or not, sorry, the pi stars, right? Just the pi's in this case, right? So that's going to be coming from here, and that's going to be coming from here. Now, the next thing that happens is that we're going to have our the sigma bonding orbital combination between the two 2p's in this case. Now, usually where that actually ends up in these homonuclear diatomics is that instead of it being below the 2p of the fluorine, it ends up being between the 2p of the fluorine and the nitrogen. And the reason for that is something that is maybe outside of the scope of the class that you're in, but it has to do with the fact that you actually have some kind of mixing of the 2s of the nitrogen as well, together with that 2p, and all of those things actually are kind of playing in together. But you would expect it to be there. Now, of course, you could also draw it where it's below the 2p of the fluorine, right? That's fine as well. Because again, what we're doing here is we're just qualitatively drawing this, right? These aren't quantitative numbers. We're not doing any kind of math to get there. But in terms of the pattern and how everything is going to organize itself out, right, you end up right here. So this is going to be then the sigma bonding orbital. And then after that, right, we would end up with the pi anti-bonding orbital up here. And then sigma bond anti-bonding orbital all the way up top. Right, and so that right there is the pattern that we have, and that right there is, the bare bones of our molecular orbital diagram. Now next, the thing that we have to do is we have to add in all of the electrons, and so if we add up how many electrons we have, right, we have 5 from the nitrogen, we have 7 from the fluorine, right, that comes out to being 12 electrons that we would expect to find in this system. And so all we have to do is just simply plug those in following the Aufbau principle, Hund's rule, and the Pauli exclusion principle, right? So we have 1, 2, 3, 4, 5. Oh, there's one too many right there. Weird. Right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right, so we have 12 electrons in here. Now what ends up, right, from what we can see here is that we actually have 2 unpaired electrons in the pi anti-bonding orbital, right, and both of those are going to be unpaired, right? So we would expect NF to actually be a paramagnetic molecule, right? So paramagnetic just simply means that you have unpaired electrons in your molecular orbital diagram, right? And so we have 2 of those in this case right here. So that's what we would expect. And so if we were then, to go and then write out our, calculate out the bond order, we can do that using the equation, right? So bond order, that's going to be equal to the number of bonding orbital electrons that we have. So in this case, we have, 2 from this sigma bonding orbital, we have 4 from this pi orbital, or these pi orbitals, right? There's 2 of them, and then we have 2 from this sigma bonding orbital, right? So we have 8 bonding electrons in this case, and then subtract out the number of anti-bonding electrons. So in our case, we have 2 from here and 2 from here, so that is 4. And so we take that, and then we just divide that number by 2. So we have then, 8 minus 4 is 4 over 2, and so that comes out to 2, right? So we would expect a bond order of 2, which matches our Lewis structure in this specific case. Now, a very important thing to point out is the Lewis structure, right, doesn't actually, tell us that we would expect to have 2 unpaired electrons, right? That we would expect to have a paramagnetic molecule. And that's kind of the power of the MO diagram, is that it does help us predict even further the reactivity and the physical properties of what we have in these cases, right? Because we're able to actually determine, right, that we would end up with 2 unpaired electrons in this instance. But that's how you approach drawing the molecular orbital diagram for a heteronuclear diatomic molecule and calculating the bond order in that case.